6 sections left for the semester, and these sections are probably the most unlike any of the sections in Chapter 4. Even the last section was more similar to the first 6 sections than the rest of them. The title of this section is Combinations, and a combination essentially is a problem where you're selecting a group of items from a set, and the order that you select the items in is not important. And that makes the techniques that we've learned so far for counting and probabilities not work so well, because the counting principle, that's where we make a set of dashes and multiply, it forces order to be important. So when we make a few dashes, it's going to make that order important. But order is not always important. For instance, in the Arizona lottery or in the Powerball, it generally says that if you match all, however many numbers, all 6 numbers, regardless of the order, then you are a winner. In the counting principle, in a problem, let's say the Arizona lottery problem, where maybe 40 balls are dropped in a bin and they're picked out one at a time, you know, how many different sets of 6 balls could come out? If you use the counting principle technique, made 6 dashes, 1 for each ball, and then you did a first ball, second, third, and you put numbers on top of those dashes and you multiply the numbers, that would mean that if these were the numbers that came up, that would be considered different than if these numbers came out in this order. And that's not the case. So what the counting principle does is it counts every ordering of a set as a different thing that it counts, and that's not always what we want to have counted. Sometimes just the numbers or just the elements themselves are the things to be counted and not the order that they come in. When the order isn't important and we just want to count the elements that are picked, then it's a combination problem. Like another example of a combination problem, say you're at an Arizona Diamondbacks game, and once every game, the I don't know if you call them cheerleaders, but some people will come and they'll throw t-shirts into the stands, and it shouldn't matter the order that you get the t-shirt in. If you're the 3rd person to catch a t-shirt or you're the 8th person to catch a t-shirt, it doesn't matter. Just the fact that you catch a t-shirt matters, and the order that you get the t-shirt in doesn't matter. That would be a combination problem conceptually. Anytime that the order something selected in doesn't matter, just being picked matters, then it's a combination problem. If an order that you're selected in matters, then it's a counting principle problem where you can make lines and multiply to get the number of possible arrangements. That's kind of what this first page says. And this second page, eventually this is going to be irrelevant because Zach Brown is, I don't even know how relevant he is now. But anyways, Holly, Sarah, Jen, and Marcia are at a Zach Brown concert. Stagehand comes up to the group and says, 3 of you can come backstage to meet the band. So in this case, if I want to say how many different ways can the 4 of them pick 3 to go backstage, the order that you're picked is not going to matter. If you were picked 1st, 2nd, or 3rd, it's just being picked 1st to go backstage. In this case, it's going to be just as good as being picked 3rd to go backstage. The fact that you go backstage and not being left out front is going to be the key here. If you did the counting principle and said, well, there were 4 people that can go first, and then once I pick one, there's 3 people to go pick second, and then once I pick a second, there's 2 people to go third, you would say there's 24 different groupings that could be picked. Well, that strategy, it counts separately, picking Holly, Sarah, and Jen, differently from picking Jen, Sarah, and Holly, and it counts that differently than Sarah, Jen, and Holly. So it's counting the order that you select the girls in, along with which girls are selected. If only which girls are selected are important, then the order is not important, it's the combination problem. It's actually not ridiculously hard to pick out the three groups of these four girls, because each group is going to be missing one girl. This group right here is missing Marcia, so that's one group that could be sent backstage, the group that's missing Marcia. Another group that could be sent backstage is a group that's missing Jen, one that's missing Sarah, one that's missing Holly. There's going to be four different groups that are possible, and I can list them here. The groups are Holly, Sarah, and Jen, that's missing Marcia, and then Holly, Sarah, and Marcia, that's missing Jen, and then Sarah, Jen, and Marshall, that's missing Holly. So I've missed Marcia, I've missed Jen, I missed Holly, but I've got Sarah in every group, so I need to miss Sarah. So the last group would be Holly, Jen, and Marcia, and that's missing Sarah. In this section, we're not going to be asked ever to list all the possible groups. We're just going to be asked how many groups are possible. And in this situation, where from four girls, I'm picking three of them to go backstage, and the order that they're selected in is not important, only the fact that they get selected is important, that makes this a combination problem. And to solve combination problems, we're going to use our calculator. There's a formula to use to solve combination problems that involves factorials, and we really don't have to know the formula. So to get the answer that there's only four groups possible, as opposed to the 24 that the counting principle gives me, I have to be able to use my calculator and know the syntax that my calculator wants. And my calculator, to do a combination problem, has that function buried under the probability. So if I hit math, arrow over to probability, you'll see that there's the NCR formula. That means C means combination, the N is the size of the group that you're picking from, and R is the number of people you're selecting from that group. So for this problem here, the size of the group is 4, there's 4 girls. It's a combination because only the girls that get picked matter, not the order that they're picked in. And I'm picking 3 of them. So in this problem, we'd say this is 4 choose 3. From the 4 girls, we're picking 3, and the order that I select them in doesn't matter. To do that on my calculator, I have to type the number 4 first, and then hit the math key, go over to the PRB, down to the NCR, hit enter on the NCR, and what this does is it calls the N4, and then I'm going to type 3, and what that does, it calls the R3, so it says I'm picking 3 of the 4 girls, and when I hit enter, it tells me how many groups are possible. It tells me that there are 4 groups possible without actually listing the 4 groups. This is going to be kind of every problem in this section that we're going to do is going to be a combination problem. It's just going to be a matter of figuring out the size of the group that we're picking from and how many people from the group or how many elements from the group that we're picking. The next few pages are just going to be basically my type up version of this lecture, and it will show you the formula for this, but I won't want to focus on the formula because we don't need to know the formula. Oh, and here are the 4 groups. This group right here is missing Marcia. This group right here is missing Jen. This group right here is missing Sarah. And this one's missing Holly. So there are 4 groups. Any other group that you could list for these 3 girls would have the same 3 girls in some other order, and we're not going to call that a different group. So the counting principle overcounts when only the objects selected are important or is important, and the order that they selected in is not important. So these problems are all combination problems. Combination is a way of selecting members from a group in such which the order doesn't matter. The formula is here. It's more complicated than I want. So the combination, what my calculator is doing is it's plugging numbers into this formula, n factorial over n minus r factorial times r factorial, idiot. For our problem, it was 4 choose 3 factorial. So what my calculator computed was 4 factorial over 4 minus 3 factorial times 3 factorial. And again, I wouldn't want to do that by hand. It's not particularly hard, but there's no reason to do it by hand when our calculator can do it way quicker and more accurately. But it's all my calculator is doing when we tell it the size of the group and how many that we're selecting. It's just taking the two numbers and shoving them into this formula and doing the math for me. All right, another example. How many different ways can 3 people from the group Dave, Dan, Julia, and Amanda, and Steve be selected to attend a meeting? So immediately when I think about problems in this section, I need to ask myself if the order the people are in selected is important or not. If I think the order is important, then it's a permutation or accounting principle problem, and I could make lines for each of the people. So in this case, we're picking 3 people. We'd go, I'm picking a first person, a second person, and a third person. I'd put numbers above the lines and I'd multiply them to get my answer. So if selecting Dan, Dave, and Julie is different than picking Dave, Julie, and Dan to attend the meeting, then you would solve the problem this way. So we have to infer from the way the problem is written whether this ordering and this ordering count as 2 different things or if they count the same. And for the way this problem is worded, I'm assuming just the fact that you're selected to attend a meeting is the important thing. It doesn't matter if you're selected first, second, or third, because each of the people that are attending the meeting, we're going to count them as equal. So all the problems in this section, we're supposed to infer that the order that the group is selected in isn't important and only being selected is important. So if I thought the order was important, there are 1, 2, 3, 4, 5 people. I'd say there's 5 people to choose from for the first, 4 for the second, and 3 from the third. That would imply picking Dan first, Dave second, and Julie first is a different grouping than picking Dave first, Julie second, and Dan third. I don't think that's the case. Usually people that are attending a meeting, there's not like a hierarchy. If you go, you go, and you're all counted as equal. And so this problem, I think, is a combination problem because I don't think the order that you were picked in is important. So it's a combination problem, and in a combination problem, I need to know the size of the group that I'm selecting from. I'm selecting from a group that has 1, 2, 3, 4, 5 people. That's going to go to the left of the combination, and I need to know how many people I'm selecting, and the number of people I'm selecting is 3. So the number of groups that can happen is 5 choose 3, and I'll just break my calculator out, type in the number 5, hit my math key, go over to PRB, down to NCR, type the number 3, and it's going to give me 10. 5 choose 3 is a real common combination. So there's 10 different groups of 3 people that can be selected. Each group is leaving out 2 people. It's picking 3 and leaving 2 out, and the order that we select them in doesn't matter. All right, next problem. 10 GCC students have applied for a scholarship. 6 students will be chosen to receive the scholarship. Again, assuming all the scholarships are for the same amount, if you're picked first or you're picked last or you're picked third, it doesn't matter. It only matters if you're selected or not. So this is a combination problem. If you made 6 lines, 1 for being selected first, 1 for being selected second, all the way up to 1 for being selected last, then you're saying the order that you get selected in is important because maybe the first scholarship is for the most amount of money and the last scholarship is for the least amount of money. And if this was the problem, there are 6 different scholarships for different amounts, then it would be appropriate to use the counting principle, make 6 dashes, put numbers above them, and multiply. But it doesn't say anything about the scholarships being different. So I'm assuming all the scholarships are the same. So I'm assuming this is a combination problem. To the left of the C is the size of the group that I'm picking from. I'm picking from 10 students that apply for the scholarship. To the right of the C is the number of the group that get selected. In this case, 6 are being selected. So it's 6 choose 10, 10 choose 6, so I'll type in 10, hit my math button, go over to PRB and down to NCR, and then do 6. and that's going to give me 210 different groups of 6 people that can be selected from the 10. All right, so now we're going to do homework, and each of the homework questions, there's kind of 2 parts to the homework. In the first half of the homework, each of the problems is supposed to be a combination problem, and we just have to figure the size of the group that we're selecting from and how many that we're selecting. So in your problem, an ice cream parlor has 20 different flavors. Cynthia's going to order a banana split that has 3 different flavors. I'm assuming if they put, like vanilla, chocolate, and strawberry, that's no different than going chocolate, strawberry, and vanilla. So this is a combination problem because only the flavors selected make a difference and not the order that they're placed in the banana split. So yours is going to be a combination. From the 20, you're picking 3, it's 20, choose 3. My problem too, a committee is looking at 8 different books, and they're going to pick 3 of them to adopt. And again, I'm assuming the order that they select the books in doesn't matter. So for me, of the 8 groups, 8 books, they're going to pick 3 of them. And assuming that doesn't matter what book they select first, second, and third, it's just the fact that it gets selected is the important part. So I'm going to type the number 8, math, probability, NCR 3, and I get 56. So I'll let you work on 3 while I do 4. Watch me do 4 if you're not sure how to do 3. So Neil wants to download 6 different songs, but he only has enough money to purchase 4. So he has 6 songs that he wants to choose from, but he only can get 4 right now. Again, I'm assuming only the 4 songs selected matter, not the order that he selects them in. So he's going to pick 4 songs and have 2 songs not selected. So this is a combination problem because just being selected is enough, and the order that you get selected in isn't important. So that's a combination of 4 of the 6, or 6 choose 4. So I'm going to go 6, math, probability, NCR 4, and I'll get 15. Clear this out now. So there are 15 different groups of songs, of 4 songs he can purchase of the 6 that he wants. Your problems, like almost all committee problems, are combination problems. And in my problem 6, I want to pick different vegetables, so I can't pick the same vegetable more than once. And I'm assuming it doesn't matter which vegetable I pick first, second, or third. It just matters which vegetables I pick. So I want to pick, of the 8 vegetables, I want to pick 3 of them. So I'm going to go 8, math, probability, NCR 3, and I get 56. So this section, just on itself in an island, it's not that bad, but when you mix the problems from the first 7 sections up in with this section, the hard part is trying to distinguish whether order is important or not. So this chapter section by itself on an island, every problem is a combination problem. There's no trickery. But it's when we mix problems that need to be solved using the counting principle and problems that need to be solved using the combination formula, that's where the whole level of difficulty ratchets up. So you have a flour problem. Me, I'm trying to make a 3-topping pizza. I can't have double toppings. Combinations wouldn't allow to pick the same thing twice. So there's a restaurant that has 10 toppings to choose from. I'm picking 3 different toppings. Again, if I picked pepperoni, onions, and olives, that would be no different than picking olives, pepperoni, and whatever I said. Idiot, I can't even remember. Nevertheless, it's a combination problem. And because the order that I pick the toppings in doesn't matter, only the toppings that I pick mattered. And also, if I was allowed to do like double olives, combinations couldn't count that. Choose 3 is $1.20. So there are 120 different 3-topping pizzas without double toppings I could pick. Your answer should be 10 for number 7. In your problem number 9, the fact that there's 2 senators from each state is a distractor. So you're trying to, from the 100 senators, make a committee of 5 senators. It's probably going to be a really large number, maybe even so much that it kind of destroys my calculator, because 100 choose 5 is a biggish number. My problem 10, there's 6 restaurants. I have time to go to 4 of them. I want to pick which 4 I go to. I'm assuming it doesn't matter which restaurant I go to first, which restaurant I go to last. I'm just going to eat at 4 of them, and 2 of them I'm not going to eat at. So it's a combination problem, and I'm assuming I'm not going to eat at the same restaurant more than once. I'm going to try 4 different restaurants from the 6. And the order that I pick them in doesn't matter, so it's 6 choose 4. Cool, it's raining right now, which is always fun. I don't know if you could hear it or not, but this room gets really loud when it rains. So you want to upload videos to whatever you watch videos with, and you have 12 videos that you'd really like to take, but you only have storage capacity for 5. That's a combination problem, because the order that you pick the videos in won't matter. You're going to pick 5 and you're going to leave 7. It matters which 5 you pick and which 7 you leave, but the order that you upload them won't matter, so that's a combination problem. How many groups of 2 7s can be made from the 4 7s in a deck of cards? I'm assuming like having the queen of 7 of spades and the 7 of diamonds is the same as having the 7 of diamonds and the 7 of spades, that the order doesn't matter when I do this as a combination problem. So it's 4 choose 2. So not all card problems are going to have a 52 in the work. They only have, well, in this case I'm only worried about the 7s, and there's only 4 7s. For your 13, it will work similar to my number 12. In my 14, how many groups of 4 hearts can be made from the 13 hearts in a deck of cards? Again, I'm assuming only the 4 cards. I'm going to pick 4 hearts and leave 9 of them out, and only the hearts selected matter, not the order that they were selected. So mine's going to be a combination of 13 choose 4. And there's 715 different groups of 4 hearts that you could make from the 13 hearts in a deck of cards, if only the 4 cards that were selected matter and not the order that they're selected in. That's the first half of this section. The not quite. That's almost the first half of this section. I actually have 3 more problems to finish out this first half. So how many groups of 13 spades could be made from the 3 spades? That's just combination problem, and the numbers are there for you. Problem 16, how many different groups of 2 black cards can be made from the 26 black cards? So I'm only focusing on the 26 black cards, and I want to get 2 of them. It's 26 choose 2. There's 325 groups of 2 black cards that can be made if I only work with the 26 black cards in a deck of cards. You'll notice that we just did a string of card problems. We didn't use the number 52 once. We're only using to the left of the C the kind of cards that we want. In this case I wanted black cards, so I only had a 26 to the left of the C. In my problem 14, I had a 13 from the left of the C because I only wanted hearts. This was really hard for me. In grad school, I had to teach this stuff, and I wanted every problem to have a 52 in it because I know there's 52 cards in a deck of cards, and yet none of these kinds of problems will have a 52 in them. So we have to be really cognizant of the numbers that are relevant in a particular problem. And I tried to, as I'm introducing this making card combination problems, I try to just put the numbers that you need just to get you thinking the right way. And then at some point, if you had to do a lot of these, we'd stop holding your hand and not give you all the numbers that you need, and it'll make it a lot harder. So 17 is your problem. And then the last group of problems in this section they're kind of combination problems where we're going to integrate the making lines from the counting principle with combinations, and it's because we're going to be selecting multiple groups in some sense. And to best illustrate how do we do both counting principle and combination problems together is probably through a problem. So at a Chinese restaurant, dinner for 8 has 3 items from column A, 4 items from column B, and 3 items from column C. And column A has 5 items. So let me try to make this in a table. It's way too wordy. The fact that there's 8 people is probably irrelevant here. So there's column A that has 5 items, and we need to choose 3. Column B has 7 items, and we need to choose 4. And column C has 6 items, and we need to choose 3. So the question is, how many different dinners are possible, picking 3 items from A, 4 from B, and 3 from C? It's going to be a heck of a lot. Each individual part is going to be a combination, because when I pick 3 of the 5 from A, I'm going to pick 3 and 2 are going to be left out. The order that I say the items I want from A aren't going to matter. I'm going to get those 3 items. So the A part, I'm going to get 3 of the 5 from A, and the order that I get them in doesn't matter. The B part, I'm going to pick 4 of the B's and leave 3 of them out, so I'm going to get 4 of the 7 from B. And for the C part, I'm going to get 3 of the 6 from C. So each one of these tells me how many different groups I can get of the A items, how many different groups I can get from the B items, and how many different groups from the C items. If I'm allowed to get 3 from A and 4 from C and 6 from C, to find out the total number of combinations, I have to multiply these. So this is going to be the integrating the skill part. I'm going to compute multiple combinations for the individual choices, and then I'm going to multiply those together. I'm going to have to do this separately on my calculator, I think. So on my calculator, I'm going to go 5 math, choose 3, which is 10, and then 7 math, choose 4, which is 35. And then 6 math, choose 3. Which is 30. So the number of different dinners having 3 items from A, 4 from B, and 6 from C are going to be 10 times 35 times 30. Which is 10,500 different dinner combinations that are possible. So you'd have to eat there 10,500 different times to get all the different possible of what's 10 items, 3 from A, 4 from B, 3 from C. So all the different possibilities, there's 10,500 of them. Every problem in the last grouping, would you look at that? I did 6, oh, look at that. That's 6, choose 3, which is, what did I do? 10 times 35, and then I had 20. Oh, this should be 20. So look at this. I couldn't even copy that number. I wrote 30 here. This should be 20. Should be 10 times 35 times 20. Sorry about that. And apparently that's only 7,000. So I overstated a little bit because I was an idiot and I couldn't copy a 30. I couldn't copy a 20. I wrote it as a 30. So should be 10 times 35 times 20, and not minus 20. And there's 7,000 different dinner combinations that you can get for a group of 8. So every problem in this section is going to work exactly like this. The last grouping of problems, we're going to have multiple combinations because we're picking from different groups. Okay, so how many groups of 3 hearts and 5 spades can be made from the 13 hearts and 13 spades in a deck of cards? So one thing that I'm doing is I'm picking 3 of 13 hearts, and the other thing I'm doing is picking 5 of 13 spades. So there's 2 groups that I'm selecting, and the order that I select the items in with cards generally doesn't matter. It's just the fact that you're selected or not. So I'm breaking in the groups that I'm selecting. First group, I'm picking 3 of 13 hearts, and to figure out how many ways to do that, that's a combination of 13, choose 3. And I'm picking 5 of 13 spades. To figure out how many ways to do that, it's 13, choose 5. And then make sure I did these right. So first I'll do 13 math, choose 3, and get 286. And then 13 math, choose 5, and get 1287. And then I'll multiply the 286 times the 1287. So we're going to do multiple combinations, as few as 2, as many probably as 4 or 5. Find out what each combination is separately equal to, and then multiply the results, because we're picking from different groups. So for your problem 19, you're making a dinner. You have 6 different dinners you can choose from. You're picking 2 of them. That's going to be one of your combinations. And you're picking a dessert. You have 3 of 5 desserts to choose from. So you're going to get 2 combinations, and you're going to multiply them together. So for my question, Tito has to write an essay on 3 of 5 questions in part 1 and 4 of 6 questions in part 2. My first combination, because it doesn't matter which order that he picks, he's going to, in the first grouping, he's going to pick 3 and leave out 2. So that's for the question 1, or part 1. And then for part 2, I'll call that question 2, he needs to pick 4 of the 6. And then 5 choose 3 is 10. 5 math choose 3 is 10. So the first probability is going to be 10, or the first number is going to be 10. And then 6 math 4 is 15. So mine's going to be 10 times 15. And there's 150 different ways. You're going to do yours essentially the same way. You're picking 6 choose 2 and 5 choose 3, and you multiply the numbers together. It might even come out to the same number. So for your problem, the club is picking girls and guys to go on a trip. You're picking 3 of the 7 guys, and you're picking 3 of the 8 girls to go on a trip. Those are the combinations that you're going to need to deal with. My problem number 20, I'm picking an 8-person committee, and in that 8-person committee, I'm going to have 6 seniors of the 10 seniors, and I'm going to have 8 juniors of the 2 juniors. So my combinations, I need a combination for the number of groups of seniors I can pick, and a combination for the number of groups of juniors. For the seniors, I'm going to pick 6 of the 10 seniors. For the juniors, I'm going to pick 2 of the 8 juniors. So I'm going to do 10 math, choose 6, and get 210. And then 8 math, choose 2, and get 28. My answer is going to be whatever 210 times 28 is. And I get 5,880. As I read your problem 23, so 12 people are going to be given a drug, 6 men and 6 women, and then there are 10 men and 6 of them are going to be given drugs, so 6 of the 10 men are going to be given the drug, and there are 9 women and 6 of the 9 women are going to be given the drug. So for your problem, you have to consider it like this. So there's 12 people being given the drug, 6 men and 6 women, and the 6 men are being chosen from 10 men. The 6 women are being chosen from 9 women. So you're going to get 2 combinations and you're going to multiply them together. So the 12s in this problem are kind of distractors. The 12 is broken up between the 6 and the 6. For my problem 22, the club wants to visit 3 of 5 landmarks from California, so I'm going to make one for California. And they want to get 3 of the 5 landmarks. And from Oregon, it's California, they want to do 2 of the 4 landmarks, because all they have time to do. 5 choose 3 is 10. 4 choose 2, I think, is 6. Yeah. So for my problem, the answer is going to be 60. You're going to go 10 choose 6 for the men, and times 9 choose 6 for the women, and whatever those 2 individual numbers come out to, you multiply them. For your problem 24, Michael has to get 5 bottles of regular soda, so you're going to make something for the regular, and he needs to get 3 different bottles of diet soda. You're going to make something for the diet. For the regular, you need to get 5 bottles of the regular, and the place has 10, so your regular is going to have the numbers 10 and 5 in it. And for the diet, you need to get 3 and there's 7, so the numbers for the diet are going to have 7 and 3. So you need to figure out for the regular, there are 10 different regulars, you need to get 5 of them. For the diet, there are 7 different diets, you need to get 3 of them. Those are the numbers that belong together in this problem. In my problem 24, a drug is going to be given to 20 people. It doesn't matter, the 20 doesn't matter, it matters that it's going to be given to 12 children and 8 adults. And so for the children, the numbers that I'm worried about, there's 15 children and 12 of them are going to be given the drug, so that's going to be a combination of 15 choose 12. And for the adults, there's 8 adults and 9 of them are going to be given it, so it's 9 choose 8. So I'm going to do each of these combinations separately. So I'm going to do 15 math choose 12, and I get 455. And I'll do 9 choose 8, which I think is 9. 9 math choose 8, which is 9. And I'll do 455 times 9. And my answer is going to be 4,095 different groups they could pick of 12 of 15 children and 8 of 9 adults. For 26, so for your problem in 27, you want to get 2 of the 4 7s and 3 of the 4 3s. Those are kind of your combinations. For my problem, I need to get 5 of the 12 beers and 4 of the 9 snacks. So for the beers, it's 12 choose 5. And for the snacks, I need to get 4 of the 9 snacks. Again, these are all combination problems because I'm assuming the order that I pick the beers in doesn't matter, just the fact that the beer gets picked is important. So I'm going to do 12 math choose 5 and get 792, and then 9 choose 4 and get 126, and 792 times 126 is 99,792. Your problem will work similarly, even though it's talking about cards as opposed to beer and snacks. How many groups of 3 kings from the 4 kings and 1 jack from the 4 jacks can be made? So I'm going to make a combination for the kings. I want to get 3 of the 4 kings, and a combination for the jacks. I want to get 1 of the 4 jacks. I think those are both 4. So 4 math choose 3 is 4, and 4 probability choose 4 math probability choose 1 is also 4. So this is 4 times 4. My 28 is going to be 16. Getting close to the end. All these card problems, you want to get 2 black cards of the 26 black cards and 4 red cards of the 26 red cards in a deck. I want to get 3 of the 13 spades and 2 of the 13 clubs. So I need a combination for my spades and a combination for my clubs. I'm getting 3 of 13 spades and 2 of 13 clubs. I don't know either of these, so it's 13 math. Choose 3 is 286. And then 13 math. Choose 2 is 78. You can't probably see those. So mine's going to be 286 times 78. Mine's going to be 22,308. Got to be getting close to the end if we're not already there. One more for me and no more for you. So I want to get 5 of 26 red card and 1 of 26 black. So for my red, it's going to be 26, choose 5. For my black, idiot. For my black, it's going to be 26, choose 1. So 26 math, probability, choose 5 is 65,780. And then 26, choose 1 has to be 26. But I'll make sure of that. So 26 math, probability, choose 1. So now I'm going to go 65,780 times 26 and get huge number, 1,710,280. So by itself, the way I've written the problems, hopefully they're pretty manageable, and it's just going to be integrating them in with the rest of the chapter. If you need to do that, that's going to be the challenge. So just one more section of new material and then just a review.